Hello guys, welcome back to TechDose, and in this video we will look at find the minimum area to cover all ones to problem, which is from Leetcode number 3197. We will be starting with the standard geometry solution which will pass our entire test cases on Leetcode, and after that we will try to optimize it using the prefix sum plus binary search technique. Now a prerequisite before solving this is to have solved the 3195, which is the first part of this problem 3197. And in order to learn about the optimization, particularly about the prefix sum, how it is applied on a 2D array, you must have done the question 304, which is range sum query 2D immutable. So I have already made a detailed explanation for both of these solutions on my YouTube channel, so you can find both the links in the description below. Now this video can be long, but if you stick around, then you will be able to understand the standard as well as the optimal solution. In this problem, you are given 2D binary array grid. You need to find 3 non-overlapping rectangles having non-zero areas with horizontal and vertical sides such that all the ones in the grid lie inside these rectangles. Return the minimum possible sum of the area of these rectangles, and note that the rectangles are allowed to touch but they cannot overlap. Okay. Now in the first example, if you see, then we can cover all the ones by using 3 rectangles, and these 3 are actually of the minimum area possible, and the total area is 5. We could have also taken this as one rectangle, second rectangle and third rectangle, but the total area would have been 6. So we need to minimize the area while covering all the ones. And we could not have taken this as one rectangle, this as second rectangle and this as third, because all the ones are not covered in this configuration. Okay, so the first thing is all the ones must be covered, and the second thing is we need to minimize the area, so we need to leave out as many zeros as we can, right? Now similarly in the second example, if you see, then we can take all these 3 items together in a single rectangle, second rectangle and third rectangle, and the minimum area would be 5 again. Whereas you could have also tried something like this, these two in one, and this is a second rectangle, third rectangle, but the area would be 6, total area would be 6. So I don't just want to cover all the ones. Yes, covering all the ones is important for correctness, but the second criteria is about minimizing the area it takes to cover all the ones. Okay, now if you look at the rows and columns, let's call the number of rows by m and the number of columns by n. Then we know that m and n both are less than equals to 30, and at least you have a single item, right? Now if you have this kind of configuration, then what can you say about the algorithm? The mn will be around 900, and if you think about the m square n square, then that will be around 30 to the power of 4, which will boil down to 81 times 10 to the power of 4, which will be around 8.1 times of 10 to the power of 5. Okay, so even if you write an m square n square algorithm, then it is going to be very less as compared to 10 to the power of 8. You can just compare it with 10 to the power of 6, right? So 10 to the power 6 is very less than 10 to the power of 8, and therefore if your time complexity happens to be around m square n square, then you will get a pass. Okay, you will get an AC for it. Now we will try to manufacture our algorithm accordingly. We know the expectations now. We are not forced to write mn or m plus n algorithms. Now in this case, the grid at ij is either 0 or 1, because this entire matrix is binary, and the input is generated such that there exist at least 3 ones. So if there are at least 3 ones, then this means that you will be always able to make 3 rectangles, right? So if you can make 3 rectangles, then this solution will always be possible. You will never get into a scenario where the solution do not exist. Okay, so I hope we have understood the problem. So let's now look at a recap of the problem 3195. In that problem, our goal was to find the minimum area to cover all the ones. So if you look at this xy axis, and let's say there are a bunch of points, and we need to cover all these points by making the minimum sized rectangle, and the rectangle side should also be parallel to the x-axis and y-axis. That was the constraint in problem number 3195. So if you happen to do that, then you can make a large box around it, and then you can try to shrink this box from all the ends. And if you try to shrink this box from all the ends, then you can shrink the top portion until it touches the topmost point. You can shrink the left portion until it touches the leftmost point. Similarly for the right portion until it touches the rightmost point, and the bottom portion until it touches the bottommost point. And we will be calling this as the low x, and this will be high x. And I will be calling this as low y, and this is the high y, right? So this will be the smallest size rectangle which will actually be containing all the dots. You can say all the binary ones, right? So our goal was to find the smallest rectangle, and the sides must be parallel to x and y axis covering all the points, and this is how we will be finding it. Now let's look at an example on applying that idea. Now in this case, the problem was about we are given a binary matrix and we have to cover all the ones by using 3 rectangles. In the previous problem 3195, we have to cover that using 1 rectangle, but here we have to cover that using 3 rectangles. So the first thing that I will be doing is, first of all, I will be finding the smallest rectangle which have all the ones. So you can use the solution of 3195 to find out the smallest rectangle which contains all the ones, and this rectangle must be parallel to the x and the y axis, and it will be parallel, right? Now once you have found this, inside it you have all the ones, as well as if you have any zeros, it is also present there. Now we need to divide this entire region into 3 parts. You can exclude some of the cells if possible, so that you can minimize the area, right? So the first thing is you need to divide these regions into 3 parts so that all the ones are covered. In how many ways can you do that? So if you think about a rectangle, and if you have to divide it into 3 rectangles, then you can divide it like this. This is one way. Or you can divide it vertically, or you can divide something like this. Okay, and you can also rotate and divide it something like this, or you can divide it in this way, or you can divide it in this way. Now if you think about, how do we know that these are only the 6 ways and there is no other way? Because if you try to divide it in any other way, like let's say you try to divide it like this and you extended it, then this will not be a rectangle. These are not 3 rectangles, okay? So this is rectangle 1, perfectly fine. Rectangle 2, perfectly fine, but this is not a rectangle. So if you want to divide one rectangle into 3 portions, then there are only 6 ways to do that. So we should keep this in mind. Now how to come up with this? Definitely you have to draw and see that you cannot have more than 6 possible ways. So there will be exactly 6 ways in which a grid of size m by n can be divided into 3 rectangles. So this grid is already a rectangle. Like let's call it a rectangle. If this grid is already a rectangle, then you can divide it into 3 rectangles in only 6 ways possible. Okay, so there will be 6 cases in this case. Now we have to try out all the cases definitely, but let me give you one option where I will say that I will be dividing this horizontally into 3 parts, and if you divide it horizontally, then we will have this as region 1, region 2 and region 3. Now will this be the entire rectangle? Will this entire region be taken as the rectangle? No, this entire region will not be taken as the rectangle. If you look at the first region, you have 0, 1, 0, 0. So if this region has to be included in just a single rectangle, then I will be trying to minimize the area and I will just include a single cell. I will be excluding the other zeros. Okay, and how do you do that? I will be again using the solution of this 3195. When where if I have a grid 0, 1, 0, 0, then find the smallest bounding box which has all the ones in it. So 3195 solution will help me here. Okay, so this will have just a single 1. Okay, so this rectangle is of size 1 by 1, so the area is 1. Again in the second region, if we apply the same logic, you will get this as the second region which is of size 1 by 3, and the total area will come out to be 3. And in the last region you will just have a total area of 1. So in this particular slicing you will get a total area of 5, 1 plus 3 plus 1. But is this the only way that you could do? No, this is just one possible way. Another possible way would be to just do vertical slicing. Now in vertical slicing you could do something like this, and if you follow this, then you have region 1, region 2 and region 3. Now in each of the region, let's consider region 1, you will just have a single cell. If you consider region 2, you will just have a single cell. Okay, so the total area is 1 plus 1 2, and in the third region you will have to take a 2 by 2 matrix. So the total area will be 1 plus 1 plus 2 by 2, which is 4. So the total area is going to be 6. So this is by one possible partitioning. Another possible partitioning could be to do something like this, where you have this as region 1, region 2, region 3. And if you do this kind of partitioning, then you will have this 1, this 2 by 2 and this 1. So the total area is going to be 6. In how many ways can we do this? Well, if we have, let's say, n number of columns, then the vertical partitioning can be done in order of n square ways. Similarly, if you have m number of rows, then the number of ways in which you can do horizontal partitioning will be order of m square ways, right? So these are the number of ways. Definitely we have to try out all the ways, and let's think about one option where you have taken this as one region where you have done the slicing like this, and in the first region you have a single one, and the second region you have single one. So the total area is 6. So I have just shown you the horizontal and vertical slicing. Let me show you one of these cases, one of these 4 cases. Okay, so let me show you what this means. This means that if I have taken something like this, I have done a partition here and I have done a partition here, right? So I have divided this into 3 regions, region 1, region 2 and region 3. If you look at all of these regions, then in this region 1, what is the size, minimum sized rectangle which covers all the 1? It is 2 by 2. So the area is going to be 4. Plus, in the second region, I can just take a 1 by 1 and cover all the 1. So the total area is 1. In the third region, I can take 1 by 1 and cover the entire 1. So this is also 1 and the total area is 6. Okay, so this is one of the cases. But is this the only case? No. Actually, you can slide this bar from the leftmost side to the rightmost side. So this is also one configuration and this is also one configuration, right? Now this configuration is invalid. Okay. Now if you consider about this configuration, then you have a 1, 1 and 2 by 2. So again the area is going to be 6. Now we can also move this bar up and we can do all this kind of slicing. So this is one slice, second slice, third slice, right? But this will be invalid because if you have this as one rectangle, then you just have 2 rectangles, right? So this is how we will be covering all the cases. If I just show you about the second case as well, then I will have this as region 1, and let's say this will create region 2, region 3 and this was region 1. So in all of these regions you can make the smallest size rectangle. This is one size, this is 1 by 1 and this is 2 by 2. So the total area is going to be 6. In this way I will be trying out for all the cases, right? Now for this case again you can do something like this. Region 1, region 2, region 3. And in all of these regions we will try to find out the smallest size rectangle which will cover all the ones in that respective region and then add up the area. So I hope this is clear. The goal is to divide the given grid into 3 regions, and we can do this in 6 ways, because if you are given a rectangle, then you can divide it into 3 rectangles in exactly 6 ways. You cannot have less or more ways. Minimize each region by getting the minimum rectangle to cover all the ones, and the solution we have to use is 3195 solution, right? Now I hope all these cases are clear, and we have also learned about how to find the minimum area. Now let's look at how to apply the vertical and horizontal slicing. So if we are given a example matrix of size 4 by 5, we need to divide it into 3 regions, and let's look at the horizontal slicing initially. So first of all, I will be finding the smallest rectangle which covers all the ones. So we already know how to find the minimum area using the solution of 3195. And in this case, once I have found it, then I will be defining a low x value. The low x value will be row number 1. The high x value will be row number 3. The low y value, this low y and high y. These all will be defining about what will be the box, smallest rectangle or the smallest box that covers all the ones initially. Now once I know that, in order to do horizontal slicing on a box, I need to divide it exactly into 3 regions. So we have to take 2 slicers. Let's call it the slicer I and let's call it the slicer J. So I can use 2 loops to iterate and find out all combinations of I and J in such a way that I will always be less than J. So if you have to move this iterator, you know that this line is low x, this last point will be high x. Okay. Now if you divide this into regions, then the first region is going to be low x to I, second region from I plus 1 to j, the third region from j plus 1 to high x, right? So this is what I am denoting here, you see. And you can easily write the 2 loops which I have written, I equals low x to less than high x minus 1, I plus plus, because you know the rectangles should not be overlapping. They can lie side by side, but they should not be overlapping, and that is how the loop will be written. J equals to I plus 1 to j less than high x and j plus plus. So this will divide your entire rectangle into 3 parts, non-overlapping part, okay? Once you have divided this, then in each of the region 1, region 2, region 3, you can try to find out the minimum sized rectangle which covers all the ones in that particular region by using the 3195 solution. That should be your idea. So if you try to divide it horizontally, then this will be one way to do that. And in the first region you will have a 2 by 2 array, and the second region you have to take 1 by 4, in the third region a 1 by 1. If you add up all the areas, 2 plus 4 plus 1 will be 7, isn't it? So it will be 7. Now, is this the only way to do horizontal slicing? Yes. In this case, there is only one way, but the total number of ways could have been the order of rho square, m square, right? And similarly, if you want to do vertical slicing, you will have to write the 2 loops, but in that case, it will not run from low x, it will run from low y, and it will not go till high x, it will go till high y. And similarly, you can do the slicing from low y to I as region 1, I plus 1 to j as region 2, and j plus 1 to high y as region 3. If I have to show you, you can do something like this. This is region 1, region 2, region 3, and in each region you apply find the minimum sized rectangle or the minimum box to cover all the ones. So 1, 1, and here you will have a 3 by 2. So total area will be 6 plus 2, which is 8. And is this the only way? No, this is not the only way. You could have done this slicing as well, or you could have done this slicing too. So the total combinations will be order of n square combinations. So this is how you do vertical and horizontal slicing. Now we have to minimize the area, and these are the 2 cases, but these are not the only 2 cases. You could have tried the other 4 cases as well. And in order to try that out, again we have to create all possible slicing using the I and j loop. Now how to do that? Let's consider how to generate all these 4 cases. We can simply run a counter from 1 to 4, and depending on whatever is the count value, I can say which case we want to solve. Let's say that the count is equals to 1 and we want to solve this case. The figure is showing here, right? Now how the loop is working in this case? If you have to do something like this, then you already know that the smallest bounding box will be pre-computed, and you know this is going to be your low x, this is going to be your high x, this is going to be your low y, and this is going to be your high y. So the entire bounding box has been made. Once the box is present, then if you want to create something like this, then you know this is your low x and this is your high x. Okay, so this slicer here runs from low x to high x. So in this loop, which value will represent this horizontal slicer? Will it be I or will it be j? If you see, the range should be from lx to hx, that means low x to high x. Now definitely it has to be I, it cannot be j. J is running from low y to high y, so it is the vertical slicer. You see this vertical slicer, this is your j and this horizontal slicer is your I. By looking at the loop itself, you will be able to know the horizontal slicer will move up and down, vertical slicer will move left and right. So accordingly you can understand. Okay, now if I have to define these three regions, then how will I do that? You think about it. Let's say that we want to divide somewhat like this. Then in this case, I will be saying that the first region will go from low x to you can say I. This is your I. So low x to I on the row side, and on the column side it will go from low y, that means this vertical line low y, which is column number 1, to j, and j is, let's say, 2. Okay, this vertical line. So from low y to j, this will show region 1. This is how we will be defining the region. If you have to define the second region, then this will be saying the x slice will be same, low x to I, the x slice will be same, row slice, whereas the column slice will be from j plus 1 means this column number 3 to high y. This is how you define region 2. And if you think about region 3, then this will be defined by, you can say, I plus 1 to high x. I plus 1 is this 3 to 3. Okay, so I plus 1 to high x, and on the column side you can say low y to high y. So this is how we can create the slicing. And if you have understood the slicing for this case 1, then I can say that you yourself will be able to create the bound for all of these three cases, case 2, case 3, case 4, right? Now this horizontal slicer will move from low x to less than high x. Why less than high x and not equals to high x? Because if I is equals to high x, then I plus 1 will go out of bound. That will not create the third region. So in order to have the third region, the I must always be less than high x, and that is why I is less than high x. And the same reasoning goes for j as well. Now I hope you have understood, and I hope you can create all the three other cases too. I will be showing you in the code how I have written all the cases. But if you find any kind of difficulty, then you can comment down below, and I will be making sure that I reply to your comment by giving you the answer. Right. Now let's move ahead and let's look at a dry run. So in this dry run, I will just be going through the horizontal and the up case because going through all the 6 cases will be too much hectic, and I think you can do that once you have understood the 2 cases themselves. So if this is the entire grid which is given, the first step is to compute the smallest bounding box. So smallest bounding box which covers all the ones is problem number 3195, and we know that this given thing is the smallest bounding box, where this is your low x, this is your high x, this is your low y, and this is your high y. Now in this case, if you do horizontal slicing, then you know how to do horizontal slicing. If you create this slice, then the smallest bound here will be 2, smallest bound here will be 1 by 4, and here it will be 1 by 1. So the total area that you have is 2 plus 4 plus 1, which will be 7. And we will not have any more horizontal slicing available. So by horizontal slicing, we will get total area of 7. If you do the up slicing, then the up slicing will be possible. Up slicing is this case, which I have already shown you, right? Previously I had shown you this case, how to create all these three regions. So you can start slicing from this and create this area. Now if you do something like this, then we have not created three rectangles, it is two rectangles. So this is the three rectangle case. Now in this case, this is 1 by 1, 1 by 1, and this is 2 by 4. So this is 8, 8 plus 2 is 10. So this combination is giving you 10, while this is invalid. Now if you go here, then you can say this is one combination. So initially you had got a 10, and now here you have 1, and here you have to cover 2 by 3, which will give you 6, 6 plus 1 7, and here you will get 1 by 1, which is 8. So this combination is giving you 8. So one combination was 10 and another one was 8. Then you can try something like this, where you will have 2 by 2, 4 plus 1, which is 9. So this is giving you 9, right? Or you can try something like this, which is giving you 6 plus 1, which is 7 plus 1, 8. So again you are getting an 8. Out of all this, you will be taking the minimum, right? Always we will try to find the lowest area. So this will be minimized. So these are the four options that you got from one combination. Again you will try the other combinations out. So if you try out everything by just trying the horizontal and up case, we got 7. You can try out all the other cases as well, and I think you will have to settle with 7. So this will be returned as the answer, saying that the lowest area which is possible in such a way that we cover all the ones by dividing this entire grid into three rectangles is 7 itself, right? So I hope this entire technique is clear. If you apply this technique, then what is the time complexity to find this bounding box, the first bounding box, that means the smallest rectangle to cover all the ones? It will be order of mn, right? Once you have done that, then what other operations are we doing? What other operations are we doing? We are actually covering 6 cases. Out of those 6 cases, 4 cases are just rotations. So this is the up case, you can say right case, up case, right case, down case, left case, which I had already shown you in the diagrams. So these are the 4 cases which are just rotation of each other, and then you have horizontal and the vertical case. If you look at the horizontal case, the number of combinations that you can form is m square and here n square. And in all of these cases, the number of combinations you form is mn combination, because this horizontal slice will have m ways and this vertical slice will have n ways, and the same will go for all these 4 cases. So this is creating mn ways, and there are 4 cases, so there will be 4 times mn, and this will be m square cases plus n square cases. And in all of these cases we have to find the smallest bounding box per region. Now how many regions are there? There are 3 regions. For each of the cases there will be 3 regions: region 1, region 2, region 3. And per region we want to find the smallest rectangle, so that will be found in mn time, isn't it? So this mn time is the solution for your 3195 problem. So if you think about the time complexity, then this is going to be, first of all you will be finding the bounding coordinate in mn time, and after that we will be covering the 4 cases, here 4 cases where you will have mn combinations, and you know that we will be solving for 3 regions and each of the solution will take mn time. So this part has come from the solution for 3195. Okay, and the other 2 cases is, this is the horizontal slicing case and this is the vertical slicing case. So if you add up the time complexity, then we will be ending up with order of m square plus n square times mn. Now if you know the calculation which I had shown you, you will end up with m cube n, and you know that the maximum value of mn is m comma n is 30. So m cube n, or you can say n cube m, can go to maximum 10 to the power of 6, which is less than 10 to the power 8. So this solution is going to pass perfectly fine, and the space complexity is just order of 1 because we are just using constant number of variables. I hope this solution is clear, and this solution will definitely pass all your test cases on Leetcode. So let's look at the code walkthrough. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we will be looking at the m square plus n square times mn solution. So this finding the bounding coordinate is the same solution as your 3195, and I hope you already know the solution. So once you know that, we will be going through the minimum sum. Okay, so this is your min function. In the minimum sum, you are given the grid, and we will be finding the smallest bounding box which will be containing all the ones. And after having done that, we will be defining the lowest area with integer maximum, that is infinity, and we will be trying to minimize the area. Then I'll be taking the current area and try to create all possible combination for the 4 cases up, right, down, left. You know how to do this, right? Now if you want to see which case it is hitting, we will be using the switch case statement in this case, and depending on the count value, I'll be hitting the case. And if it is the up case, you know what is the diagram. This is the up case, and you know that one of the horizontal slicer will move from low x to the last. So this is low x, this is I, and this is the high x. So how do you define the first region, region 1? It will be from low x to I, and then you will have low y to j, low x to I and low y to j in the given grid. How do you define the region 2? It will be from j plus 1 till the high y in the y side, and in the x side will be same. You see low x to I and j plus 1 to high y. And how do you define region 3? It will be I plus 1 to high x, I plus 1 to high x, and low y to high y. Okay, so this is region 3. If you think about the right case, then this is the diagram for your right case. And this is your low x, this is your high x, this is your low y, and this is your high y. Okay, so this is your I, this is your I iterator. Here you have the I. Okay, and this is your j. So how do you define this region 1? This region 1 will be defined by low x to high x and low y to j. Low x to high x and low y to j. How do you define this region 2? It will be from low x to I and j plus 1 to high y. Low x to I, j plus 1 to high y. And how do you define this region 3? It will be from I plus 1 to high x and j plus 1 to high y. I plus 1 to high x and j plus 1 to high y. Right? So this is how you can also understand about the down and the left cases. So once you have defined all the region, you have to find the minimum area, and finding the minimum area is actually the same solution as we have seen in 3195. Okay, now this part of the code is very similar to this find the bounding coordinates, very similar. So in this case as well, I will be finding in the entire rectangle, if you have certain ones and a lot of zeros, okay, any number of ones and zeros, then you need to find the smallest bounding box. Shrink this box, find the smallest bounding box which contains all the ones. So this solution and this solution is same as your 3195. So since it is a prerequisite, I hope you have already seen that, and once you have found the smallest bounding box, you can find the area by multiplying the two sides, the length and the breadth. So this is your find minimum area, and out of these 4 cases, we will always be trying to minimize the lowest area, and that's what we are doing here. Okay, now I have already shown you how to create horizontal slicing, and you will have order of m square combination for that, and for each of the combination you have to find the minimum area and minimize the lowest area. Similarly, for the vertical slicing, you will have n square combinations for it and try to minimize the lowest area. So this is your standard solution which will definitely pass all the given test cases in the problem, but we can optimize it even further. If you look at the find min area here, then it is saying about if the region in which we are trying to find the smallest box, if it has all zeros initially, then the smallest box size will be 0. The area will be 0 in such case. So can we answer if the area will be 0 or not in just order of one time instead of answering it in order of mn time? Here we are taking mn time. Even though the entire region has all zeros, we have to go through the entire process, go through both the loops in mn time, and then we will be answering that whether you have you even have a single one or not. But this can be answered in just O1 time. How it can be answered? It can be answered if we have created a prefix sum on this 2D matrix. The prefix sum will have all the zeros. So just by looking at the last cell, you know that if the prefix sum is 0, then that means you do not have any item in the entire 2D array. And that's how you can simply return in order of one time, having pre-computed the prefix sum, that the bound is not possible. The area will be 0. So this will be one optimization, that whether I should even run this part of the code or I should not. Okay, so this is done by the prefix sum, and the prerequisite for that is to solve the problem number 304, where I have already explained in detail how to apply 2D prefix sum on a 2D matrix, right? So this problem is very important to apply this optimization and understand it. But still I will be giving you a recap. Okay, so this is one thing that you can do. Now let me show you the prefix sum optimization. So let's see this prefix sum optimization. In this case I have taken a grid and I will be finding the smallest bounding box. Yes, you know, I will be applying the simple approach, order of mn, to find the smallest bounding box which contains all the ones. So I will get low x, low y, high x, high y in this case. Now I will also be doing one more thing as a pre-computation, which is to find prefix sum. I will take one extra row which is dummy and one extra column which is dummy. The concept for taking the dummy is the same as in the single dimensional prefix sum, where you know that if you have n size, then you will be taking from 0 to n, where the 0 is the dummy, so that if you want to find the range sum in the range of, let's say, L to R, then you can always do prefix sum at R minus prefix sum at L minus 1. And even if L is 0, you will not go at a negative index, right? You will not go out of bound. So that same concept will be applied on 2D as well, and that is the reason we are taking a dummy row and the dummy column. Now what are these values? What is this value 3 here? This value 3 says that if you find the prefix sum of this box where it is ending, the bottom right corner is ending at 2, 3, then the count of ones will be equals to 3. That's what this 3 is saying about. Okay, so it is about the bottom right corner of the entire box. So if you think it logically, bottom right corner, how to compute? What should be the formulation for computation? So the formulation should be the prefix sum at this point will be equals to the prefix sum that you see up, which is actually equals to the sum for this entire box. This entire box here. So let me change the color so that it's visible easily. So prefix sum for this entire box, then you have to take the sum for this portion, which is the prefix sum of this entire box. Okay, then you have to add this value, whatever is this value, the grid at ij. Okay, so this value is 0, so this has to be added. What is the prefix sum here? It is 2 plus what is the prefix sum here? It is 2 plus what is the grid value here? 0. Okay, now if you see, this region has been added 2 times, so it needs to be subtracted 1 time, isn't it? It needs to be subtracted. Therefore we need to subtract this portion, the prefix sum here. So this prefix sum needs to be subtracted, so minus 1. So it will be equals to 3, and this will give you the count of total ones in this bounding box ending at this index 3, 4. In this case it will be 2, 3, right? The count of ones ending at 2, 3. So this entire detailed explanation has been done in 304, and if you want to find the count of ones in a range, then it will be possible. How to query that within the range of PQ and RS, how many ones are present? How many ones are present? How do you know that? So it will be the prefix sum of this entire box. You take this entire box prefix sum and you subtract this portion here. So this entire box will be prefix sum at r plus 1 s plus 1, because if you are looking at rs in the original grid, then you are looking at r plus 1 s plus 1, because we have added one dummy row and dummy column which is 0 0. So the counting is based on 1 here. So that is why the prefix sum at r plus 1 s plus 1 will give you the total count in this entire box, and then you subtract this value here. Let's say it is x. And what is this value? What will be the row number? The row number here will be p. Okay, row number will be p, and the column number will be s plus 1, and you have to subtract this box as well. Let's say this is y value here. So how to get this? It will be prefix sum at r plus 1 row. Okay, so this row r plus 1, and the column will be q. Okay, you have to subtract this, and when you subtracted it, you have double subtracted this value. So if you have double subtracted, you have to add it one time. So add this value, and what is this value? It is prefix sum at pq. So if you do that, then you will get the prefix sum of this bounding box here. So this is the technique to do prefix sum query on 2D. And if you apply this, then you can optimize this function here, finding the minimum area, by not iterating through it directly, but you can just cover this case right in the beginning and answer in O1 time if the answer will be 0 or non-zero. And if the answer is non-zero, then you can write this piece of code and try to solve it. So if you ask me where is the optimization, in amortized time you will not find optimization, but yes, you will find it in runtime. Okay, so if you just apply prefix sum. But if you apply prefix sum with binary search technique, then you can avoid these two loops directly, and you can introduce a log order in your solution instead of doing linear search. So what is the idea of applying this binary search? If you think about the idea of applying binary search, then it's based on, let's say that you have a box here. Okay, you have a box here, and this is your low x. So I'll just name it lx, low x, high x, and there are a bunch of ones and zeros. Now if I want to find the minimum size rectangle which contains all the ones, then let's say that here you had all the zeros, here you had all the zeros, okay, here you had 1, and you had ones, you have zeros and ones. Okay, so this is, let's say, row number 0, 1, 2, 3, 4. I want to find the minimum row bound. Okay, minimum row bound. Where should be the lx value? That means the low x value in this case. So what I will define is a min x value, and the min x value will say it should actually end up saying 1. Okay, because I want to say that this slice will be the one which will contain all the ones, right? So this is called your min x, and this is called your max x. I am explaining according to the code, how I have written the code. Okay, so initially let's say lx and hx value are given, or you can say x1 and x2 values are given, whatever it is, in whatever way you understand it. So let's say x1, x2 value are given. Now what you can do is, I will be defining low value to x1 and high value to x2. You could have easily done linear search and tried to skip. If the row has all zeros, then I will skip that row. Or how do you apply the linear search, by the way? You know the prefix sum, and prefix sum at this point will be 0. So you can just look at the prefix sum at the end value, and you will be knowing about where you have zeros. So prefix sum at this point will be 0. Prefix sum at this point will be 2. So as soon as you see a non-zero prefix sum, you can stop and say this will be the min x. And for finding the max x means where will be the bound on the lower side, the higher side. You can go in the reverse order, and if the prefix sum comes out to be the same, like if the prefix sum here is a, here you have a, and here you have b. So as soon as it changes, then you can stop at the previous one and say this will be the bounding box. but this is a linear search. Okay, linear search will be order of m, where m is the number of rows, but you can improve it. You can improve it and solve it by binary search. If you apply prefix sum, you will solve it linearly. If you don't apply anything, then you might have to go through entire mn solution, whereas if you apply prefix sum, you have to solve it in order of m time. But if you apply binary search, you can solve it in log m time. So there is an improvement from mn by using prefix sum. I mean, the simple solution will be mn solution. If you apply prefix sum, then it will be order of m solution, and if you apply binary search, then it will be log m solution. How to apply binary search in this case? You find the mid value. Okay, you have defined low value as x1, high value as x2. Define the mid value. Once you know the mid value, at this midpoint you just need to see about the prefix sum at this value. Okay, so if the prefix sum here says 0, this means there are no ones here. So where should your min x go? It should go on the lower side. Okay, but since in this case the prefix sum here will be greater than 0, that means there are ones, so your upper slice must go up. So your upper slice min x will be defined with this mid value, and your high value will become mid minus 1, and your search region will be in between 0 and 1. Now again, if you calculate mid, it will come here, and if you see the prefix sum here will be 0, that means I should go on the lower side, which means that at this point until this row there are no ones, so I will be skipping it. Okay, and then your low will become mid plus 1. So your low high being same, the mid comes here, and if you see the prefix sum here at this point will be greater than 0, and so your min x will be reassigned to this mid value, which is 1, and then you will go up, and the high becomes less than low, so you will stop and your min x will stop at 1. This is how you will choose where to stop for min x. Similarly, just applying similar logic, but the movement logic will be separate. You can find the max x. How to find max x? You will be starting with the low value at 0, the high value being at 4, and your mid value will come here. Okay, now your max x will be assigned to minus 1 value or 0, whatever it is. You will have to find out the prefix sum value at this point. If the prefix sum value here is greater than 0, then this means that there are ones on the top, so min x must be above, and if this value is greater than 0, then I need to move down. Okay, I need to move down. Now if you move down, then your max x will be assigned to this mid value, your low will be assigned to mid plus 1, high is here. So again, if you find the mid, your mid value will be at low at this 3, and if you find the prefix sum here, then this will be greater than 0, and you will find that okay, I need to set the mx here, that means the max x, and I need to move down. When I find prefix sum, then I'm not saying the prefix sum of the entire matrix, but the prefix sum only in the bound of LH bound. Okay, and that I can easily do by using this formulation, that how to find prefix sum in a bound. Okay, so that's what I will be doing. I will be moving down, and when the L and H are here, the prefix sum will be 0 in this bound, and that is where the H will move up, and so your mx, the final max x, will be at 3, and this is how you will select the bound. Okay, so I hope you have got the idea of how to find the minimum area using the binary search. So this is one of the code logic. I have made a grid, and you can imagine this will be the prefix sum which you can compute from the grid in mn time. Now once you have computed that, our goal is to find the smallest rectangle to cover all the ones. So find mean area is the function that we will be writing, and I need to find out the low x, low y, high x, high y, isn't it? So I can apply this logic. This is the code implementation for finding the min x, right? So I'll be initializing min x equals to x2, which is 3, and then I will be trying to move up, because min x will always move up. It is the topmost line. So min x should stop at 1, and the max x here will stop at 3, right? So this is a min x implementation. I think you can go through and understand. Once you apply this implementation, then you know that the time complexity will change. The prefix sum will take order of mn to build the array. Then computing the bounds, I will just do a simple implementation. You could also do the binary search implementation, but since it is not involved in more complex time complexity, so I just kept it simple. It will be mn, and the four cases where each of the case combination will be mn combinations, and there will be 3 times find min area in that. We will be solving each of them in log order. Okay, and this is the vertical and horizontal slicing cases. So the only difference in time complexity is this portion, which is making it logarithmic order. And so once you do that, then the final time complexity will be m square plus n square plus mn times of log m plus log n. And this is much more better, much improved version as compared to your simple solution. But we are incurring a space complexity of mn due to the prefix sum. I hope it is clear. Let me now show you the code. In this solution, we are taking the prefix sum and we are computing it as we had done in the 304 range sum query 2D immutable solution. Once you do that, we can always get the box sum in the range of x1 y1 and x2 y2 by using the prefix sum 2D query, the range sum query. Once you know that, then you know how to find the bounding coordinate. It is the same as the previous solution, and we have a new solution for the find min area. If you look at the min function, the structuring of the min function will not change. It is the same. If you scroll through, it will be the same structuring and finally returning the lowest area by going through all the cases. So here the entire skeleton is same, but the only change is in the computing the prefix sum. This is extra, and there is a major change in the find min area. So if you look at the find min area, then you know that if a box is given, then how to find the bound, the min x, min y, and the max x and max y. I have already shown you the dry run with code implementation for this min x. You can understand the max x, min y, and max y as well. So there will be 4 binary searches, and each of them, whatever is running on the row, the min x and max x is running on row. So this will be log of m, 2 times log of m, and the ones running on the column, that is min y and max y, will be 2 times log of n. And that is why this factor actually came into the complexity part, right? So I hope this entire solution is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.